So in last lecture we discussed how to interface a memory with a processor and how to assign the addresses. And in today's lecture we will discuss general operation of a processor, how a processor operates. Right? So already we discussed that inside a processor or inside a central processing unit there are general purpose registers where we can store the data. There is timing and control unit which is used to generate various signals which are used for proper operation of a central processing unit or a processor. And apart from this, we are having arithmetic and logical unit. Now we will slightly elaborate this with this diagram. As I told you, the purpose of registers is to store the content, store the data. And we already discussed that. Suppose if this is one memory, this is suppose one RAM or ROM, and in this RAM and ROM also we store the data. So what is the difference between this storing place and the registers? So basically the storing place of this memory, suppose these are the storing place, right? These are the locations 0, 1, 2. So here we access these locations by its address. For example, location 0 is having address 0000H in hexadecimal number system. Location 1 is having an address 0001H, like this. So to access this location 0, we have to use this address. But in case of registers, registers are the part of processor. It is inside processor. Where is this memory? It is outside a processor. So inside a processor we are having registers which are storing place, and some special name is given by the designer of particular processor to those registers. To access those registers we have to use those names. So I will take one general example. Suppose there is one processor. In that processor there is a register named as A. Okay. There is another register named as B. There is third register named as C, and there is fourth register named as D. So we are taking an example. Suppose there is a processor. Inside that processor there are 4 registers, and the name of these registers are A, B, C and D. Now these registers can be a 8-bit register or 16-bit register or 32-bit register or 64-bit register. So here the meaning of 8-bit register means 8-bit of data can be stored in this register. 8-bit data can be stored in this register. And if this register is a 16-bit register, then we can store 16-bit data inside this register. So now for an example, we will take these registers as a 8-bit register. Right? So this register is 8-bit register. So all of these registers can store 8-bit of data. Now what else is there inside a processor? Inside a processor, we already discussed, inside a processor there is a timing and control unit. There is timing and control unit. Now I will add another thing here, decoder. Decoder, timing and control unit. Now here, what is the purpose of decoder? So decoder is used to decode the instruction. Instruction is used just to tell the processor what it has to perform, and that particular thing will be decoded by decoder. So decoder will decode the meaning of instruction. After decoding the instruction, timing and control unit will generate various types of control signals. So example of control signal is read signal, write signal. So this timing and control unit will generate control signal. Right? Examples are read signal, write signal. Okay. Now, there is one register called as PC, program counter. Program counter. The purpose of program counter is it points the next memory location from where processor is going to fetch the next instruction. So program counter points the next memory location. Why it will point the memory location? Because whatever program we have written, we have to load that program in the memory, in the ROM. So now let us assume this is our ROM or code memory. Right? So whatever program we will write, so that program will be loaded in this code memory. And this program counter will point that memory location from where this processor will fetch the next instruction. Right? Now let us assume this program counter is of 16-bit. Why it is 16-bit? Because we have assumed that this processor, whatever processor we have taken, this processor is of 16-bit address lines. This processor is having 16-bit address lines. So if it is having 16-bit address lines, then we can connect here a memory of maximum 64 KB. 64 KB memory can be connected. Right? How do we come to the conclusion that 64 KB memory can be connected? So for that, 2 raised to the power number of address lines, that is 16. If you calculate this, then it will be 65,536. So these many locations. So with 16 address lines of this processor, we can access total 65,536 locations. Now, at each location, we can store 1 byte. That's why in 65,536 locations, we can store 65,536 bytes. And in computer terminology, 65,536 is termed as 64K, 64,000. And in the last we put B, byte. So the maximum memory capacity for a processor having 16 address lines will be 64 KB. That's why we have connected here one memory of 64 KB. Memory we have connected. Now to access the locations of these 64 KB memory, since there are 16 address lines, so the addresses will be of 16-bit, right? For example, here this address 0000H. So H means this is a hexadecimal number. If you convert this hexadecimal number in binary number, then 1 0 of hexadecimal will have 4 zeros of binary. This 0 of hexadecimal will have 4 zeros of binary. This will have 4 zeros of binary. And this will have 4 zeros of binary. So in total these are 16 bits. So memory location number 0 will be addressed by these 16 zeros. That's why this location address will be pointed by this PC. Due to that, this program counter is a 16-bit register because it is going to point the memory location, and memory location address is of 16-bit, right? Okay. Now, this is okay. First, we will see this. This PC will send the 16-bit address of your memory through these address lines. So these are our address lines. Address lines. These are 16. And this is unidirectional. Now this is our data line. So, and this is bidirectional. Now let us assume that our this journal processor, which we are discussing right now, this is a This is a 8-bit processor. So the meaning of 8-bit processor is, at a time, it can fetch, it can take, or it can send only 8-bit of data. If the processor is 16-bit, then at a time it can send or it can receive 16-bit of data. If a processor is of 32-bit, then at a time it can send or receive 32-bit of data. So let us assume, for our this explanation, this processor is a 8-bit processor. So if this processor is a 8-bit processor, then the data lines of this processor will be 8-bit. So this is 8-bit data line. So there are 8 wires over which data will flow. This address line is 16-bit. This means there are 16 lines, 16 wires over which address will flow. So now this data line, internal to this processor, there will be data lines. So let us assume this is the internal data line of the processor, right? 8-bit. This is connected to register A. This is connected to register B. All these 8 lines. There will be 8 lines. There will be 8 lines. Because the basic architecture of this processor is an 8-bit. Right? Because for this example, we are taking a processor of 8-bit processor. That's why all these data buses are of 8-bit. Now there is arithmetic and logical unit. So suppose this is one arithmetic and logical unit. So this is our ALU, arithmetic and logical unit. Now the basic architecture of this arithmetic and logical unit is also 8-bit, because we are taking a 8-bit processor. So here this 8-bit ALU can receive 2 8-bit numbers, and it can perform addition over those 2 8-bit numbers. It can perform subtraction over 2 8-bit numbers, or it can perform multiplication or division on 2 8-bit numbers, or it can perform logical operations like AND or XOR over 2 8-bit numbers. After performing the arithmetic and logical operation, it generates an output. So we are having two inputs, two 8-bit inputs. So this is 8-bit input, this is also 8-bit input. So these inputs are coming from these data buses. After performing the operation, it will generate the output, and there will be only one output. Suppose two numbers, we want to add two numbers. So after the addition, we will get one result. So that result will also be 8-bit. So this is a 8-bit result. And this will be again connected to this 8-bit data bus. So this is internal to our processor. This is our microprocessor. Right. Now this is the internal architecture of one general purpose microprocessor. I have taken one processor. Now depending upon company to company, the internal architecture may vary. Some processors may have A, B, C, D, E, F general purpose registers. Some may have these general purpose registers as a 16-bit general purpose registers, right? So internally it may vary. Just to understand the basic operation, we have taken this particular example. Now at the output side, at the outside of the processor, we are having one ROM, that is read-only memory. And as we know that since there are 16 address lines of this processor, so maximum we can connect 64 KB of memory. So let us assume we have connected all the 64 KB memory. This is 64 KB ROM we have connected. So this is location number 0, 1, like this. The last location is 65,535, because as I told you, for a 16-bit address lines, we can access 65,536 locations. So since we are starting the location with location number 0, that's why the last location will be 65,535. And the starting address of this first location will be 0000H, and the address of last location will be FFFFH. Now these address lines will be connected to address lines of the processor, and this data line, this memory is having 8-bit data line. Because at each location we can store 8-bit of data. So those 8 bits will come out from this memory from 8 different data lines. So this memory is having 8-bit data line. So this 8-bit data line will be connected to the 8-bit data line of the processor. And this timing and control unit will generate control signals like read bar, write bar, and some other signals are also generated by timing and control unit, but we will take those signals in coming lectures. Now since this is a ROM, So here we have CS bar chip select. To select this memory, this pin must receive binary 0. So this I will connect to ground. Now, since this is wrong, so here we have another pin named as read bar. So read bar is connected to read bar of microprocessor. So from those that signal of read bar which is generated by this control signal, timing and control unit, right? It is connected. So in this way we will interface. Now here, how this processor will operate. Suppose we want to perform the addition of two numbers. Then how this processor will perform that addition. Now in order to tell the processor that you have to do this, we have to write a program. And whatever program we have written, that must be understood by this processor. Now, this processor is a digital processor. This is a digital processor because all the internal architecture we have manufactured with the help of digital components. That's why it is a digital processor. And it can perform digital operation as well as it can understand only digital values. So now, how to write a program so that it should be understood by this processor. So now, when we talk about the programming language, then there are basically three types of programming languages. One is machine language. So machine language is a language which is written in form of binary values like 0 and 1. So here we write this with the help of binary 0 and binary 1. So in early days, people used to write a program by using machine language. Now you just understand one thing. Suppose we want to perform the addition of two 8-bit numbers and those numbers are already stored in register A and register B. Let us take one example. Suppose those two numbers are already stored in register A and register B. And we want to perform the addition of these two numbers. So now we have to give some instruction to this processor that you add two numbers which are already stored in A and B. After receiving that instruction, this processor, what it will do? It will bring out the 8-bit number which is in A through these data bus and it will available here to this ALU as first number which has to be added with second number. Now the second number is in B, it will come out from these 8-bit data bus and from here it will be available to this ALU as second number. Now these two numbers are available here. Now inside the ALU, we already discussed that we can perform operation of addition, subtraction, multiplication, division, or we can perform the arithmetic operation like AND logic, OR logic, XOR logic, like this, many operations can be performed. So inside this ALU, the designer of this particular processor, who have designed this processor, already they have fabricated inside this ALU one 8-bit adder section. Right? So already you have studied about adder, subtractor, all these logics in the previous previous class subjects like digital logic design or digital electronics. So for adder, now since this is a 8-bit ALU, so it can perform addition over two 8-bit numbers. Suppose there are two numbers 1001 1110. This is your first number, and let us assume the second number is 10000001. We want to add these two numbers. So how to add these two numbers? So to add first number 0 and 1, you require here half adder. Now after adding these two numbers, there may be possibility that some carry may be generated. Some carry may be generated and it will come to this next digit addition. So when you are adding the next two bits, this and this, at that time there may be possibility that there may be some carry. In this case, particular example, 0 plus 1 will not generate any carry. But suppose in place of 0, 1 was there, then 1 plus 1 will be 0 and carry will be generated. So that's why we have to, we cannot use here half adder to add this particular bit, because here there may be possibility of carries also there. That's why to perform addition over this second bit, you require one full adder. Now same way, there may be possibility when you are adding these two bits, one carry is generated. So here also you require one full adder. Here also you require full adder, like this. At every addition point you require full adders. So now when you want to perform addition over two 8-bit numbers, then basically we require 7 full adders and 1 half adder. In place of half adder, here also we can use full adder, and in that case we can keep the carry input of that full adder grounded, 0. So now this type of circuit, 7 full adder and 1 half adder or 8 full adders are already fabricated inside this arithmetic and logical unit by that company who has fabricated and designed this particular processor. Same way to perform the subtraction, there will be a subtractor unit which perform the subtraction over two 8-bit number. And again remember, since this is a 8-bit processor, that's why it can perform only addition on two 8-bit numbers at a time. So there will be adder section, there will be subtractor section, there will be multiplier which can multiply two 8-bit number, there will be divider, there will be AND logic section. So inside, basically I want to say that inside this ALU there are many electronics are fabricated. Now out of those many electronics, which particular electronic will be utilized by us, how we will indicate that to this processor? So that will be indicated by our program, right? So, right. So now let us assume that if we want to add two numbers which are in A and which are in B, suppose this binary combination of 8-bit 1 0 0 0 1 1 1 1. This 8-bit binary combination, this will indicate addition of A plus B. Means whenever this binary pattern enters inside the processor, then first it will go to the decoder section. Decoder section will decode the meaning of this binary pattern. And the meaning of this binary pattern is processor has to perform the addition over A and B. Then automatically, internally, the content of A, which is a 8-bit number, will come out over this data line and it will be available over first input of this ALU. The content of B will be available as second input of this ALU. And out of many logics inside this ALU, like addition, subtraction, division, multiplication, addition logic will be activated and addition of these two numbers will be performed by those adders and result will be generated. And again, the result is available over this data bus. And finally, suppose in this processor, we want that whenever we complete any addition, after the addition, whatever result is generated, that result is stored in A. Always the result of addition or subtraction or multiplication always will be stored in A. So again, it will be stored in A. And suppose if we want to add the content of register A with content of register C, then there will be some different binary pattern which will perform addition over A and C. Let us assume for that 1 0 0 0 1 1 1 0. Suppose this binary pattern. If this binary pattern enters in this processor to the decoder section, then decoder section will decode this binary pattern as addition has to be performed over content of A and content of C. So in that case, the content of A will be available to the ALU and content of C will be available to the ALU. Right? And suppose if you want to add content of A with content of D, then there will be some different pattern. 1 0 0 0 1 1 0 1. Suppose this pattern, whenever this pattern, binary pattern enters in the processor, it will be decoded by the decoder. Then decoder will immediately come to know that processor has to perform the addition of register A with register D. In that case, content of A and content of D will be available to the ALU. So, depending upon the internal architecture of a processor, there will be a binary pattern which defines particular operation of a processor. And when a programmer writes a program by using these binary patterns, then that program is called as machine language program. So machine language program is machine dependent. So what is the meaning of machine dependent? Machine dependent means for this particular machine, whenever this particular binary pattern enters in the processor, then addition of register A and register B will take place. Maybe there may be chances that some other company, suppose company Y, company Y has designed a processor in which this binary pattern may add the content of A with content of E, because in that processor maybe there is another register, E register, and with this binary pattern they want to add the content of A with content of B. That's why if we are using this processor, we have to use the machine language of this particular processor only. If we are using processor of company Y, then there may be different meaning for the same binary pattern for different processor. So same program you cannot run on other processor. That's why whenever we are writing a machine language program, that is program in binary form, those programs are machine dependent. So this is machine dependent. This program written for this processor will not run on another processor, because the meaning of binary pattern may change in some other processor due to the change in internal architecture of that particular processor. That's why this language is machine dependent language. And machine dependent language is also called as low level language. Low level language. The meaning of low level means here we are dealing with low level, at the architecture level of a processor. So with the help of machine language, we are writing a program at the architecture level of a processor. So in early days, people were used to write a program with the help of machine language, right? But writing a program in machine language is very slow process, because you have to write many zeros and ones, and it is very much possibility is there that sometimes, suppose if you are writing 010101, there are 1001 we are writing, there may be chances that somewhere we may miss the values, right? So there may be always chance of errors when we are writing program in machine language, and it is very much tedious job. So what happened later on, people designed assembly language. Assembly language, right? So in assembly language, we have to use mnemonics. Mnemonics are English-like word which indicates the operation of particular instruction. For example, just now we discussed 1 0 0 0 1 1 1 1. Suppose this is used to perform addition on A and B. Right? This binary pattern is used to perform addition over A and B. A and B content has to be added. So now what the designer of this particular processor they have done, they have given some name to this binary sequence. Since this binary sequence is used to add content of A and B, so they have given it one name as add A, B. Right? So this is mnemonic. So this is mnemonic, add A, B. With this, now if you write a program by using mnemonic, then in place of this binary pattern, we can write add A, B. Just by seeing this, so these are English-like word, add is an English word. So with just by seeing this, we will come to know that this instruction is used to add the content of A with content of B, and finally the result will be stored in A. Now another binary pattern, this 1 0 0 0 1 1 1 0. Suppose this is used to add A and D. This binary pattern is used to A and D. So the designer of this processor has given one mnemonic for this particular binary pattern, and that is add A, D. So when we write add A, D, then the processor will perform the operation of addition of A with addition of D, and final result will be stored in A. Right? So now with the help of these mnemonics, we can write a program in assembly language. But again, if we write this program add A, B, then how this processor will understand the meaning of add A, B? Because this processor is a digital processor, it can understand only binary sequence. So it is not possible for a processor to understand this. Only for the ease of the programmer, these mnemonics have been designed, and programmers are using now these mnemonics in place of binary zeros. Right? So again, this assembly language program is again machine dependent, because we have written instruction add A, B. Now if same instruction we will write in and for another process, suppose there is another processor Y. In that processor A register is of suppose 16 bit and B is of 16 bit, or there may be some other registers. So there may be chance that this particular mnemonics cannot be used for another processor, because this is again machine dependent. So assembly language program is also machine dependent. So these two languages are low level language, because in these languages we are writing a program on the basis of architecture of a processor. Right? Now the third programming language is high level language, and this is machine independent. For example, language C. So when we write a program in language C, at that time we never mention we have to add the content of A register or B register or C register or D register. Simply we write a statement. Right? Now, once writing a program in C language, we have to convert that program as per the processor, as per the machine, by using compiler. Now compiler will convert that high level language program to that particular processor. Right? So in this way, there are basically three types of programming languages: machine language, assembly language, and high level language. And initially programmers, they used to write a program by using machine language, but since the machine language, in machine language there is always chance of the error and it is a slow process. That's why the designer of these processors, they have designed the assembly language program. In assembly language program, we have to write the mnemonics, and with the help of mnemonics, programmer, they have to write a program. And after that, there is a high level language. In the high level language, we have to write the statement which is not dependent upon the architecture of a processor, but we have to use a compiler. That compiler will convert that particular program in C into that particular specific processor machine language. Right? So this is the basic interfacing of a processor and some internal logic of a processor with the memory. Now in the next lecture we will just see with one example how this processor will perform one simple task of addition of two numbers. So that we will discuss in next lecture.